Hello and welcome back to my next video. So I'm just gonna mess around for a minute. Just kind of zoom in and out maybe just to create a better, yeah. Okay, so this seems to be a good angle where you well, I do apologize. Let me just put that down. I want to like get in close, but unless I push it up like this is like the only way. Okay, so we'll just do this then, and I'll just move it up and down as we go. I have enough room now. It's kind of steady. I don't know. It's a balancing act at this point. It's on a selfie stick. Okay, but that doesn't matter. So today we're going to be doing 3.1 measures of variation and dispersion. And I have been pushing this off because it's such a prolonged chapter. One of the, you might not be able to see it, but it's right up here. So right here, measure right here. There you go. So it's kind of a fun task getting through this. I'm kind of in a weird way because the camera's in front of me, so it's kind of watching as I do this. So today we're going to measure variation and dispersion, and it's a very long note. We are going to go through variance, standard deviation, the empirical rule, and range. And that's a lot in one video. So we're going to go much more conceptual, as said before. I've got the calculator right here. I've got my highlighter. I've got pen. We're just going to take off from here. So when we look at, so last time we looked at central tendency. Now we're going to take a different look. So whenever you have a spread of numbers, or a list of numbers, you're going to have something called dispersion, a measure of how spread out the observations are, or like variety among it. So yesterday we did the list 1, 2, 3, 4, and 5. Very simple. Okay? We looked at all of the measure of tendencies. So the medians in the middle, the modes. There is no mode, but the median and mean are in the middle. So it's equal on both sides. When you look at it from the mean, it's even on the lower half and the upper half, so that's good. But what follows from this is a entirely different perspective. And so when we look at central tendency, we look at the center. But when we look at variation and dispersion, we look at everything. So that's more of a perspective that we're gonna be taking with this section. And so what we can do with this is that, remember, everything that's going to be put out here is a different interpretation of dispersion. It doesn't mean that it's wrong, it just means that it's distinct from the others and needs to be taken in a serious manner sometimes, but finding it in others problematic. So the first thing that generally you come across in a Algebra 1 or Algebra 2 course, when you're looking at mean, median, and mode, you might also look at range. Range is a very easy concept. It's just the difference between the largest and smallest values. It's the idea here that if you have the maximum minus the minimum, you're going to show us the full continuous spectrum of all of it. So you can find them on the TID84 or TI84. So we did a video last time to show you. It's very simple. All you do is you go in here and you're going to look. So you might be able to see it. So you're going to go to Stat, you're going to go to Edit, and then you've got your numbers right here. Then you're going to go to Stat again, and that's how you edit, is Stat and Edit. That edits the list. Then you're going to go to First Variable Statistics. I don't think we'll get to Second Variable Statistics, but First Variable we'll use. And then we're just going to go down. We're going to do this. So we see our mean, and then we're going to continue down. We see our summation. We see the summation squared a little bit. Well, that's not the summation squared, but because, yep, that's... So we have the minimum is 1, the maximum is 5. And then the range is, well, it's not on here then. It should be 4, because you just take that minus that. But you can find the minimum and the maximum. So that's pretty much what you can do, is you can find it on here, but you have to kind of do it yourself. It doesn't, but that's just how it is. The following are a sample of scores, right here. Sample of scores from 2 classes, and they're all in percentages. So you have an algebra and a stats class. So we just computated the mean, and then we just computated this. We took 100, which is the top, which is the only top. So for every relative frequency distribution list or whatnot, it's always going to be 100 at the top. Nothing can go above it. So what we did was we found it for algebra. So it's 74 for algebra as the mean, and then we took 100 minus 60 equals 40. And if you don't know how to computate the mean of any given set of numbers, that's best to go back to 3.1 and look that over. Then what we have is the range of statistics, which is just 40. So then down here it says label the mean and the range of the exams of a dot plot below. So we have 2 dot plots, and the mean is right here. So we labeled it, and then the range is full. The ranges are the same, 60 to 100, and that's important, but it's not nearly as important as the means. So, if the means of 2 data sets are the same, does that mean the data sets are similar? No, they may have different points. And this is true. The central tendency does not dictate location of points. Dispersion, though, on the other hand, does dictate the distance from min to max. If the ranges of 2 data sets are the same, does that mean that the data sets are similar? The distance from min to max, but the data points in the interior could be different otherwise. Range is not a sophisticated measure of spread, and it is not resistant to outliers. And that's another point that you gotta make, is that it is not resistant. So the difference between most of the central tendencies and the measures of variation is that the measure of variation look at the entire whole and can show you the range of points, like with range, or you can find the center. So the center doesn't really dictate much. It dictates the fulcrum point, but the um, not the variation. And that's a big distinction. Okay. So, we are going to be getting into the big and sour parts of this. So, range is kind of easy. We kind of flew through it. It's not too hard. But standard deviation is the biggest pain of life. Not that it's a pain to do, because it's very easy to actually compute, but it's very hard to understand, at least in my perspective. When I was taught standard deviation before this, and I had no idea what it means. And now I'm going into this, and it's kind of relevant, but again, this is even like we haven't even gotten into probability yet, so this is kind of like the sections before. So, right now it says compute the range, standard deviation, and variance of a variable from raw data. And so this is just the essay or the stats exam scores. So we have to look at deviation. And so the one problem that I have with standard deviation, and we can go over here and look at these notes first before we get to the other ones, is what is standard deviation, what is variance, and how do those kind of interconnect with each other on an actual conceptual level. Because when you're taught this stuff, you're taught, these are the same thing, but how? And that's more of a question that I ask. So with variance, you have a measure of how spread out an entire data set is. Now, the variance is a bit hard to explain because it's so much more sophisticated than range. Range is just, how spread out everything is, and then you've got this as like it just, you know what I mean, it kind of confuses me because, if variance is different than range, then what makes them so different? If you're giving me these vague definitions, then it doesn't count. But nevertheless, variance is the measure of how spread out it is, and it is used more in advanced statistics. it is used more in advanced statistics. I think we might get into more of it in the later chapters when we get to there. However, it is quite problematic. It's, we don't use it much in, I think, the Stats 1 course, but I know that it is quite, it's complex, very complex, and so we're not described that, so it confuses me. So these are the formulas for variance. I'm not going to get into deep what the variance is. We can find it. We'll look down here at notes of what they are and what happens and how we compute them. But it's difficult because, you've got problems. So let's take a look back over here before we get into standard deviation. So what ends up happening within any given set is that deviation from the mean is the difference between each observation and the mean. And if we interpret the mean as being the fulcrum point, then think of it as, we have, let's say, our fulcrum points right here. How far is this from the fulcrum point? How far is this? How far is this? How far is this? How far is this? And we find that deviation by just taking this number. It's just the difference. It's similar to range. It's in a more reductionist approach. It is the range from 65 to the fulcrum point or the mean. Okay. So when we have a deviation, so these are all the deviation numbers. Okay. And so when you have all these deviation numbers, they're showing you kind of the range between each. And you've got some that have big ranges and some that have small ranges. And the thing about deviation is that this is pretty much the range between, one point and the fulcrum, but it's hard to analyze a little bit. So I'm kind of going off right now. Let me just explain. So deviation is deviating from the mean. Okay. So here, when we summarize, when we're trying, let's say we take all of them and we want to know the average of the deviation. So how far each and every deviation, how far they are. What is the average that a specific number will be? And when we try to find that, because we're trying to find the mean of the deviation. So we're trying to find the mean of the deviation from the mean. So what we do is we look at deviation, okay, and we square it. Because when we summarize them all together, or not summarize, but when we add them up, we get 0. And that's because what ends up happening is that each point essentially cancels itself out. Because the mean, remember, is the fulcrum point. So the mean is going to be 0. Okay? So the summation is, at least when looking at deviation. So if we put these out on a plot, 0 would be the center, and that's because 0 is the fulcrum point. It's still the fulcrum point, except what we're doing is we're taking another set of numbers to explain our set of numbers. And it's kind of complex, but it's interesting, because 0 is still the fulcrum point. It's still the mean. And so when you add it all together, you're just going to get 0, because so when let's say we take all these numbers and we graph them. I'm going to go up here a little bit. Oops, I just tipped you a little bit. There we go. So let's say I graph this up here. Okay, so this is the deviation from the mean. So the mean is the fulcrum point. So you're going to have points out here, and it is represented at 0, remember. And then you have it out here. So this out here is essentially, each point is separated. This is how far it is from the mean. Some are close, some are far. But overall, when you add them up together, you're always going to get 0, because each point is going to counteract another point. And so that's kind of an interesting observation to make, but it's something that's essential to standard deviation. So let's say we tried to find the average of the deviation. Now we can't really find the average of the deviation by the deviations themselves. Because if we're going to find the mean of the deviation about the mean, which is a very, like, what do you mean? So we're going to square it. And we're going to square it to make it all positive numbers, and thus the mean, this is still the mean, technically. So it isn't really the essential, well, no, it's not the mean, but this is the mean. And that's because each point counteracts the other point. And it's a weird observation to make, something that I've just kind of gone with. It might be something different, though, you know. You could always look at it and think, you know, when I'm trying to add them all up and I just get one number, it's quite interesting. But it creates a problem. It means we can't find the mean of the deviation about the mean. And the mean of the deviation about the mean is the standard deviation. And so when you look at standard deviation is the standard for which each point deviates. It's the average number that each point would deviate. And it's a very special number because what this does is we can interpret it. The point about computing, because many of these numbers, if we looked at it frankly, we wouldn't need these numbers, you know? But when you look at the numbers, when you look at standard deviation, you can understand and infer. And that's the important part, is we're taking a list of numbers and we're creating a system to which we can interpret it. And that's the basics of statistics. Statistics is looking at lists of numbers and showing you how we can interpret specific findings from this. And from just one list of numbers, we can find tons of information. So compute this. So let's go to C. What information does the sign of the deviation convey? So the sign conveys the positive deviation value above the mean and the negative deviation value below. So that's the value below the mean. So what the sign of a deviation conveys, what information does the sign of a deviation convey? Yes, so it conveys that if it's above or below the mean. Think of it like this. It's the range of it from the fulcrum point. So if I'm on a teeter-totter, and the fulcrum point we know is in the middle, okay, it would be kind of interesting for the teeter-totter to be uneven, where one side is longer and the other is shorter. So if I was trying to have a teeter-totter and my side was longer than the other person's, like that would make it awkward. It would be difficult because it's, well, that's more force, but it'd be difficult because, you know, you've got the position. But, sorry, I went off. So what I can do is I can say, how far am I from the fulcrum point? How far am I from the middle? And it's not that it's the middle of the upper half and the lower half, it's the middle of the fulcrum point, the exact center to which all of the numbers are. We want to find average deviation because that would tell us about how far all the scores were from the mean. What is the problem with adding the deviations and dividing how many there are? What can we mathematically do to fix this? Again, so the sum of the deviations is always 0 since the mean is the balancing point. That's the point given. So we should square all the deviations to them positive and then find the sum. And that sum kind of changes it. Now, why we do that, I don't know. But, you know, that's a point of inquiry. So then we're going to go over here. So I'm going to explain variance a little bit. Then we're going to get into the points about standard deviation. How these two are interrelated, but we don't know why. That's just it. They're found different ways as well, so it kind of interesting. But it is what it is. So now that we understand deviation from the mean, we can understand variance. Let me just fix this. Sorry about that. So when we look at variance, you know, we have the population variance and we have the sample variance. Big distinction. So if you're noticing here, it's different signs actually. You've got the n and the n minus 1. This comes, we haven't gotten to 1.1, we will get to 1.1, do not worry. But the point of this is that the idea here is the sample variance and the population variance are going to show you how spread out they are, but in a more advanced sense. So in the standard deviation, we find it in a different way than most others because it's pretty much similar to mean. We do this and then we divide by n or with a sample. And we divide by n1. I don't remember why, so I'm not going to get deep into that. But with the standard deviation, it's the summary, or it's the mean just to the square root. So if you look back here at mean, we know that mean is, oops. So we know that mean is this. So mean is the summation of all of the numbers, or the numbers we're trying to find the mean of, divided by the actual quantity of all of the numbers. While the standard deviation is a bit different. So it actually takes the deviation, so it takes the number, the initial number, minus the mean. So remember, this is the mean right here. So the initial number minus the mean, which is going to give us the deviation. Then we square the deviation in order for us to find it. Then we add them all together, and then we divide by n. Now this is for population. For this one, it's a little bit different. So you have the x bar mean instead of the um, Greek symbol. But it's the same thing, except down here you have n minus 1. That's something to do with the distinction between population and sample. And it's important later on. So another interesting thing is that the standard deviation is actually the square root of the variance. And that's something that I will note here. And the variance is just the standard deviation squared. And the relationship is fuzzy. We don't get into it because we're just introduced to this, but I will look into it more later on when we probably get into more chapters, or if I take another stats course. Just like the mean, there are two flavors. Yes, there are. There are population and there are sample. Down here. So the symbols are a little bit different. You've got the S symbols for sample, and then you've got the, I don't remember, I don't know, was it omega? I don't remember, but it was a Greek symbol. So the symbols of population are sometimes called unadjusted in computer outputs. I'm not going to get into why. I don't remember. I'm going to be honest. Yeah, I'm a little fuzzy on some of the details about these notes. This is more of a review. So let's just continue. Variance and standard deviation are always negative, or non-negative, and that's because we square the deviation, so it will never equal 0, or the lowest it can be is 0. But because it has to be non-negative. I don't know why the variance, but I know why the standard deviation, and that's because we squared it, and the squared is going to get rid of any sort of negative, for at least the mathematical sense. Why we square it, I don't know. Variance and standard deviation are not resistant to skewing or outliers. And why is because they are based upon the mean. So because they are built off of the mean, they're going to be non-resistant, they're going to be able to move. If I put a bunch on one point of the fulcrum's going to move a little bit. It's either going to tip one way or, it's not. So it is not resistant. So, and that's because it's just built off of the mean. It's a variable that is very related to the mean. Standard deviation, both the population and the sample, has the same units as the original data. And that's because I don't know why, but we can just go with it. Variation has the original data sets squared. We don't use variance for interpretation very much because, I don't know why, but you know, it just is what it is. We will never calculate variance or nor standard deviation by hand. And that's because it takes so long. You know, this took, maybe 10 to 15 minutes. And we're not even done yet. You know, we still haven't divided by the n, and we haven't done the square root because it's so long. So you never really do it by hand. I did it once when I was in my sophomore year. It wasn't fun. It was actually a pain. And I thought it was going to be on the final test, but you know, it would have taken forever to do. So the calculator finds both standard deviations when you run one variable stats. And your calculator does not find variance directly. Instead, you need to use this relationship. Standard deviation equals the square root of variance, and the variance equals the standard deviation squared. That's about it. So the big point that I want to make here is the interpretation. So with the interpretation, um, why do we have these numbers? That's probably a question you might ask. And the reason is, when you have a large standard deviation, it means that the mean for how spread it out it is bigger. So the mean of the deviation about the mean is bigger, which means it is way more spread out. And this is a key point to make. This is a big point. So it's showing you that there's a lot of spread, or there's a little spread. So standard deviation can be thought as roughly the give or take from the mean, or how far the range from the fulcrum in a symmetric data set. In other words, most data falls within a standard deviation of the mean. So the standard deviation of the mean it shows that most of it, when you're interpreting it, will fall within its range. So what it shows you is that the deviation from the mean is going to be, this much. And that might not be a lot, but it'll be this much. Variance, there is not a practical interpretation of variance. Instead, it's a measure that's used in later chapters and mathematical formulas. So again, we will get to that later. So we are going to do, let's take a look at what we're going to do. We kind of have to do everything. So, see, there's quite a lot here. Maybe, no, actually, no, I mean the 3.3, I do apologize. Let's take a look. So we do need to go over the empirical rule. Okay, so we'll just get chapter 3, or we'll just get example 3, and then we'll go into this muddy waters. Okay, so find the population variance. So we just kind of found the population, the sample, the population, the sample. What variance and standard deviation, which variance and standard deviation, population, or sample are more appropriate in the situation? Explain. So this is actually a sample, because remember, it's not a population. It's not of all SAT, or not SAT, I do apologize, not all stat exams fall under this. So it's going to fall into that category of not being a part of a population. So the standard deviation for sample would be more appropriate. Okay. Is the answer for C is a parameter or a statistic? It's a parameter because it's from a population. Letter G. Interpret the mean and standard deviation for the statistics data set in the context of the situation. We expect a random statistic student's exam score to be about 74 points, give or take 13.98. So let's take a look at these numbers, and then let's interpret it similar to this. So the 77.4 is actually the mean, okay? So that was already, I think, computed before. Now, what it means is, let's take a look at these scores. So find the population standard deviation, and then find the sample. So the sample standard deviation, okay, right here, that is showing us how far it is away, or how the standard mean of all of the deviations is going to be about 13.968 points. And that means that when we look at it on a graph of some sort, we're looking at it and we're thinking, you have a deviation of about this much. So anything that kind of goes out of that is going to be maybe a bit unusual because it's not the standard that we can find. So when it says down here, we expect a random statistics student's exam score to be about 74 points, give or take 13.968 points. So this is the mean. So we're expecting the score to be about, but there's a little bit of lenience here. It could be above 13.968 points, or it could be below. And that's important to understand because it sets a range of what is the standard. So let's go back to our teeter totter. So if we're on the teeter totter again, and we know where the mean is, okay, the mean is the fulcrum point. There is a deviation, a standard deviation of how far the things will most likely. Now the standard deviation should cover most of them, but sometimes it won't cover all of them. And then, yeah, you can just find the range from this. Are any of the test scores unusual? So this is another important part about interpreting it. So we're going to look at these important notes right here. If a data set is beyond 2 standard deviations away from the mean of a symmetric distribution, it is considered unusual. This is more of a technical terminology, but it needs to be understood. So whenever you have a standard deviation, okay, you're going to have some of them that are going to be outside, okay, and that's going to be standard. That's going to be something that's normal, okay, and it goes from 1 to even 2 because you got a little bit more lenience there. I don't know why it's 2 standard deviations, but I know it is. So what ends up happening is very large values is the mean plus 2 of the standard deviations above, and a very unusual or very small unusual values are below the mean by 2 standard deviations. So in the context of this, the unusual one would be uh, it would be close to the 100 um, mark because this is about 26 and that's about 74, so that's a bit around 100, while below it is about 46, I believe, or something related, maybe 48. So, and that's more because you have 13.968, and you added it, or you multiplied it by 2, like up here. So you multiply it by 2, and then you added it to this mean. And what you get is anything above this is considered unusual. And anything below this is considered unusual because it doesn't fit the rest of the scores. But none of the scores um, are unusual. So that's unfortunate, but it is what it is. Oh, let's fix this. Okay. Consider the following data sets which all have the same. Oh, whoops! I do apologize. So here's a little picture here. So when we have our standard deviation as our fulcrum point. Okay, and what this shows us is that there's a bit of lenience when it comes to considering what's unusual. And so this is unusual out here. So this is all considered like normal distribution. We would generally consider this to be a normal thing. And when you have smaller standard deviations, you have a shorter amount of lenience. But with this, you have greater lenience because of such a bigger range. So if you understand that if you have a lower standard deviation, I'm just putting that up in this corner right here. You might not be able to see it. Yes. So a lower standard deviation decreases the lenience or the range of, and I keep on saying lenience, it's more of a range. I'm saying lenience in the terminology of range because it's technical terminology, So it's kind of more of a lenient, but I don't know. So I'm saying lenience, but it's more of a range. It's actually range. So it's worse to say lenience. It's saying the range of unusual decreases, and it's the same with standard deviation. And that's just because it sets up um those borders. Okay. If any range of datasets constitutes less than 5 proportion of all data, then it is considered unusual. Less than 1% proportion is considered very unusual. Okay, so example 4. Consider the following datasets which all have the same mean. What is it? Rank the datasets from the smallest standard deviation to the largest standard deviation. So remember, looking at standard deviation as an interpretation is how more spread out of the data, the higher the standard deviation. So let's take a look. And it wants us to put them in ranking them. So it's kind of already here. Okay. So it's kind of already right here in front of us, graph 2, 1, and 3. And why is that? Well, right here, this can be considered your focal point, but you've got, you don't have an even distribution. You have a very uneven distribution. You have kind of like an exponential decay and then an exponential growth. And down here, you have something even dissimilar. It's, um, this is a little bit more, I guess, appropriate because it will follow the more of the empirical rule. But you have more of a exponential decay or exponential growth, and then like an exponential decay. And then right here, you kind of have just a linear line. So all the data sets have a mean of 4. Okay, they all have the mean of 4. But what is the smallest? And then what is the largest? So it says right here that graph 2 is actually the smallest standard deviation, okay, because the dispersion of it is not very spread out. It is uneven, but it's not very spread out. So why is that? Well, that's because you have less in the middle, less by the mean, and you have more on one side, making it lopsided, and the other is also lopsided. While this graph right here, you don't really have, um, you have more dispersion because it's more lopsided up here, but there's even marks as you go down. While up here, it's the exact opposite. And then this is more of a quote from the text, but this is like the Goldilocks. It's the even distribution. Okay, there's very even, not a lot of dispersion, but yeah. So, or well, there's a good amount of dispersion, but not as much as this. So, actually, no, I do apologize. Let me rephrase all of this again. So, just let's go through. So I'm thinking about this all wrong. So down here it says the larger spread more values, uh, far from center. So what this is saying is that when we're looking at dispersion, how far away is it from the mean? So this is very far from the mean because they're all lopsided. This is not because they're all on that focal point. This is a bit of an even distribution and it kind of falls in the middle. That's why there's this is why this is second, this is first, and this is third, is because of that dispersion. I do apologize, I was thinking about it all wrong and I just went about it in a crazy way. Okay. So down here, okay, we're just gonna do A and B, I do believe. Yep, that's all we're gonna do. So example 5. The following chart allows 6 normal curves, all with different standard deviations. The graphs have the same x and y axis scales. Match the graphs to their standard deviations. Okay. So remember, when we're interpreting standard deviation, we're going to interpret it as the deviation, the mean of the deviation for the mean. Okay? And so when you have a lower standard deviation, you're going to have less dispersion from the mean, and if it's more spread out, you're going to have more. So let's take a look at this one. This is zero point 0.5 because it's all on that center piece right here. This is the mean. Remember, this is the fulcrum point of all of them is right here. Excuse my lines. So what's going to happen is that when we look at them, 0.5, 0.75, it's just ordering them in the way because they slowly start to get flatter and then the standard deviation goes up. So the relationship that it's trying to explain here on the graph is that the higher the standard deviation, then it's going to be the more spread out it's going to be. So that's going to show you more spread out. So it's going to have a higher dispersion from the mean. Now I'm kind of getting myself a little bit confused at least when I was going through the notes. So when I was looking at the mean and I was saying, well, the mean or the standard deviation is the mean of the deviation from the mean. What does that necessarily mean? Because, it's kind of a little of an unnecessary number. Well, it's a number that's interpreted. So that's a big thing. And it's interpreted by being the dispersion from the mean. And you might be thinking, you have no idea what you're talking about. Why are you doing these videos? The point of it is that I'm trying to show a relationship, and I'm having a hard time doing it. I'm also bouncing all around, so do apologize for that. So, but when it comes to specific points that I'm trying to make, is that when you look at it, this is going to have, because the deviation from the mean is not as big, and the standard deviation from the mean is not as big as well. I do apologize for that. Okay. What do these graphs show that the standard deviation and variance measures? Standard deviation measures spread. The more spread out the data is, the larger the standard deviation slash variance is. That is the relationship. Okay, I think we are on to our final point. So we are going to get into the empirical rule. What time are we at? We're at 42 minutes. Okay, has anyone watched it all? Not a single soul. Okay, that's fine. I'm gonna put these videos online for the next week, and then I'm taking them off as unlisted. These videos are not very professional. I do apologize. I'm trying to understand it as much as I can. I'm still having a little bit of a problem of understanding the standard deviation as the mean of the standard or the deviation from the mean, and how that how that relates to the mean. But all of these are going to be taken off. This is just for me to get myself together. They're going to be unlisted. So I will probably do that on Sunday. So these will be up for the next 5 days. So let's just go over the empirical rule and then kind of understand. So here is where it kind of gets a bit confusing. So we've proved, or we've attempted to prove, I haven't proved in anything because, there's no explanation of why, there's just it is, and that's kind of what frustrates me about, textbooks is that this is this way, and, there's no reason why it is, it just is. And that's something that kind of infiltrates me. Not that it's not that there's no theory, because there is, but at the same time, why? Why is there this amount of dispersion from the mean related to the standard deviation, though the standard deviation is the actual mean from the deviation of the mean? I don't know, maybe I'm looking into it too complexly, maybe I'm just not looking into it enough. I don't know. Okay, so the empirical rule is an actual rule that ends up happening when you have a bell-shaped normal distribution. Now, when we looked at let's just draw a graph up here. Okay, you may be able to see it. Yes, you can. So it's a wonderful graph, let me tell you. So you have over here, you got all these, and then you got down here. So we had, as our median, we had um, 3. 3 was our median. And then over here, we kind of had 4. And this is more a frequency graph, but let's just look at it as it is. Okay? This is a graph of um, this is a graph of the standard deviation from the mean. It's more about that than it is about anything else. And that's what this graph is down here. It's showing you the relationship. So the empirical rule states that if a distribution is roughly bell-shaped, doesn't have to be exactly, but roughly, then approximately 68% of the data will lie within one standard deviation of the mean. Approximately 95% of the data will lie within 2 standard deviations of the mean, and approximately 99.7% of the data will lie within 3 standard deviations of the mean. If this data set is not roughly bell-shaped, if it is skewed right, skewed left, bimodal, multimodal, or anything else that's weird and crazy, then the empirical rule does not apply. And what this is showing is it's showing the relationship between having um, a consistent dispersion with the with the standard deviation. So what is this? I do apologize. When I question these, I don't understand. I don't understand why the empirical rule is what it is. Apparently, it just is. I understand what it's saying. I understand everything between ins and outs. Yet, I still don't understand the very pragmatic or the very process of what it necessarily entails. So that's why when I'm trying to go on and go on these rambles about this is what it is, it really isn't. Okay, so I'm just gonna list the notes. The x-axis is a horizontal asymptote. It cannot touch it. You cannot have 0% data. Symmetric around the mean. So the mean is the vertical line down the middle. It is symmetric on both sides. So this is kind of our line of symmetry. And that's how you draw it. The first standard deviation falls from 68%. So it falls at these, what they're called inflection points. So these are, they place vertical lines at each point, and it's a line about halfway. So this is what is showing the first standard deviation. For problems with the empirical rule, keep the standard deviation lines vertical and even. It's the same thing that we went over in 2.4. If you start creating weird things with the graphs, it's just gonna mess up. Label each section with the appropriate percentages. That's true, you need to show the relationship. And label the vertical line with appropriate x values. That is the values right here. So what this graph is showing is this graph is showing the relationship between a normal distribution and the standard deviation. And it follows this relationship, the empirical rule. So, here we go. So, in a survey conducted by the National Center for Human Statistics, or Health Statistics, the sample mean height of women in the U.S. ages 20 to 29 was 64 inches, with a sample standard deviation of 2.75 inches. Assume that the heights of women in the U.S. are normally distributed. Construct an appropriate and accurate normal distribution with the parameters and percentages labeled. Hint, shapes, scale, numbers, and percents all matter when drawing. And so what you do with this relationship is you're going to label the percentages inside. I generally do that. Then you're going to label all of the standard deviations about the mean. Okay. And then the scale of it is also important too, because if it's lopsided, it's going to look bad. So these are the same thing we went over in, I think, 2.1. Yes, it was 2.1. So in 2.1, we kind of went through the graphs and we looked at them and I explained what they all mean. So estimate the percent of women that are between 64 and 69.5 inches. So we see that between 64 and 69.5, we have 47.5%, roughly half, is between this. Okay, and that's just looking at the graph and getting information off of it. Estimate the percentage of women that are taller than 69.5 inches. So it's going to be 2.5%. You're just going to add 2.35 and 0.015. Estimate the percent of women that are taller than 64. It's just going to be 50%. Remember, all of it on the wrong side is going to be 50. Okay, let's take a look. Estimate the percent of women that is between 61.25, which is about right here, and 72.75. So you're taking this number, so you've got 68 plus 13.5, which is down here a little bit more, right here, plus 13.5, plus 2.35, plus 0.15, well, no, not 0.15, because that's on the outside, is 83.85. And then what heights for women would be considered unusual? And we can understand this from right here. So what is unusual is this is the first standard deviation, this is the second. Anything this way and anything this way is unusual. So that's just the wrap up on it. I want to do a little bit of a recap. So what we went through today was we kind of went on a lovely journey through the depths of my despair. But other than that, we went through range very quickly. We went through standard deviation and variance, and we had a few questions. I had a few inquiries into it, like what is variance? Why is variance important? Why don't we look at variance? Why is it always, or well, why is it the same units, etc., etc. We also looked at unusual values of the technical terminology of using that. Then we looked at the empirical rule. Don't know why the relationship exists or how it exists or what is proof of its existence, but it does, and we're just going to go with it because this is statistics. It's not statistical thinking. So that's just it. It's showing a relationship between the normal distribution of things and the standard deviations. There may be more of these out there. I don't know. We might have to see. And then we just did an example. So we went through unusual and usual today. We went through variance and standard deviation and range. So that will conclude 3.1. I will see you guys all back here for 3.2. I will see you all back here for 4.1. I'm sorry.